Look up at the night sky. What do you see? Stars, planets, the pale brush of the Milky Way stretching across the darkness. But you're only seeing 5% of what's really there. The rest, 85% of all matter in the universe, is invisible. It doesn't shine, it doesn't reflect light, it doesn't interact with anything we can touch or see. And yet, it's everywhere. It's passing through you right now. Trillions upon trillions of particles streaming through the Earth, through your body, through the very screen you're watching this on. Undetected, unfelt, unknown. We call it dark matter, and it's not just floating out there in the void. It forms a vast cosmic web, a hidden architecture that stretches across billions of light years, holding galaxies together, shaping the very structure of reality itself. This is the story of the universe's greatest mystery, the invisible scaffolding upon which everything you've ever known is built. Welcome to the Deep Drift. The mystery began in the 1930s, not with a telescope pointing at distant galaxies, but with mathematics, with numbers that refuse to add up. A Swiss astronomer named Fritz Zwicky was studying the Coma Cluster, a massive collection of over 1,000 galaxies bound together by gravity. He measured how fast these galaxies were moving, and then he calculated how much mass would be needed to hold them together. The numbers didn't match. The galaxies were moving far too fast. At those speeds, they should have been flung apart eons ago, scattered across the cosmos like leaves in a hurricane. But they weren't. Something was holding them together, something with enormous gravitational pull, something invisible. Zwicky called it dunkle Materie, dark matter, but the scientific community wasn't ready to listen. 40 years later, in the 1970s, astronomer Vera Rubin turned her telescope to spiral galaxies. She wanted to understand how they rotated. The expectation was simple. Stars closer to the galactic center should orbit faster, while stars on the outer edges should orbit slower. Just like planets in our solar system, Mercury races around the Sun, Neptune crawls. That's how gravity works. But that's not what Rubin found. Instead, stars at the edge of galaxies were moving just as fast as those near the center. The rotation curves were flat, impossibly flat. It was as if the galaxy was embedded in something much larger, something that extended far beyond the visible stars and gas, a vast, invisible halo. Rubin's observations changed everything. This wasn't an anomaly, it wasn't a quirk of one strange cluster. This was universal. Every galaxy they looked at showed the same pattern. Either our understanding of gravity was fundamentally wrong, or the universe was full of matter we couldn't see. Dark matter. And it wasn't just present, it was dominant. For every gram of ordinary matter in the universe, the atoms that make up stars, planets, you, there were 5 grams of this mysterious invisible substance. The evidence didn't stop with rotation curves. Once astronomers knew what to look for, they found dark matter's fingerprints everywhere. First, gravitational lensing. Einstein predicted it. His theory of general relativity showed that massive objects bend space-time itself. Light traveling near something massive, a star, a galaxy, a cluster, curves around it, like a river bending around a boulder. When we look at distant galaxy clusters, we sometimes see strange arcs and rings of light, distorted images of galaxies far beyond them, their light bent and magnified by the cluster's gravity. But here's the thing. When astronomers calculate the mass of these clusters based on visible matter, the stars, the gas, everything they can detect, it's not enough, not nearly enough to produce the lensing effects they observe. But if you add dark matter, vast halos of invisible mass surrounding and permeating these clusters, the numbers work perfectly. The light bends exactly as it should. Then there's the bullet cluster. In the early 2000s, astronomers observed something extraordinary. Two galaxy clusters that had collided and passed through each other. The hot gas, visible in X-ray telescopes, had slowed down, creating a shockwave where the clusters met. But the mass, measured through gravitational lensing, hadn't stopped. The gravitational centers had sailed right through the collision, completely separated from the visible matter. It was like watching a ghost walk through a wall. Dark matter, unaffected by the electromagnetic forces that govern normal matter, had simply passed through. And then there's the cosmic microwave background. This is the afterglow of the Big Bang itself, light that's been traveling for 13.8 billion years, now stretched and cooled into microwave radiation. When we map it, we see tiny temperature fluctuations, tiny ripples. These ripples are seeds, the quantum fluctuations that would eventually grow into galaxies, clusters, and the large-scale structure of the universe. But the pattern of these ripples tells us something crucial. The way they're distributed, the sizes of the hot and cold spots, these depend on the composition of the early universe. And the data is crystal clear. Normal matter, atoms, everything we can see, makes up only about 5% of the universe's total energy density. Dark matter, 27%. The rest, dark energy, is another story entirely. But what matters here is this. The cosmic microwave background is a baby picture of the universe, and it shows that dark matter was there from the very beginning. Now imagine zooming out. You're leaving Earth, passing the Moon, Mars, Jupiter, beyond the asteroid belt, past Neptune into the darkness of interstellar space. You're leaving the Milky Way now. Our galaxy shrinks behind you, a spiral of 200 billion stars glowing in the void, but you keep going. Past Andromeda, past the local group, out into the vast cosmic ocean. And as you zoom out further, you begin to see something. A pattern. Galaxies aren't scattered randomly across the universe. They're arranged, clustered, connected. They sit along vast filaments, threads of structure stretching across hundreds of millions of light years. Between these filaments, voids, enormous empty spaces, darker than the deepest ocean trenches. This is the cosmic web, and it's woven from dark matter. In the early universe, dark matter began clumping together, pulled by its own gravity. It couldn't collapse into dense objects like stars. It doesn't interact electromagnetically, so it can't radiate energy away. Instead, it formed vast, diffuse halos. And normal matter, gas, hydrogen, helium, fell into these halos, drawn by their gravitational wells. The gas compressed, heated, ignited. Stars were born. Galaxies formed inside dark matter scaffolding, like cities built along ancient riverbeds, following invisible waterways carved into the bedrock of space-time itself. We can simulate this. Cosmologists run massive computer simulations, modeling billions of years of cosmic evolution. They start with the initial conditions, the tiny density fluctuations from the early universe. They let gravity do its work. And what emerges is breathtaking. The cosmic web forms naturally. Filaments connect nodes where clusters of galaxies gather. Voids expand as matter is pulled into denser regions. The simulated universe looks almost identical to what we observe. When we map the real universe using surveys like the Sloan Digital Sky Survey, we see the same structure, the same web. But here's what's humbling. We can only see the galaxies, the bright points of light, the filaments themselves, the dark matter threads connecting everything. We can only infer them. The cosmic web is invisible. We're like sailors in the ancient world, mapping coastlines and islands, unaware of the vast ocean floor beneath us. Except the ocean floor in this case is what holds everything together. So, what is it? If dark matter is everywhere, if it outweighs ordinary matter 5 to 1, if it forms the backbone of cosmic structure, what is it made of? This is one of the most pressing questions in all of physics, and after decades of searching, we still don't know. The leading candidate is something called WIMPs, weakly interacting massive particles. These are hypothetical particles that only interact through gravity and the weak nuclear force. They'd be heavy, tens or hundreds of times the mass of a proton, but they'd barely touch anything. If WIMPs exist, billions of them pass through every square centimeter of your body every second, and you'd never feel a thing. Scientists have built detectors deep underground, in mines beneath mountains, shielded from cosmic rays and background radiation. These detectors contain ultra-pure materials, liquid xenon, germanium crystals, kept at temperatures near absolute zero. They're waiting for a WIMP to collide with an atomic nucleus. Just once, a tiny flash of light, a minuscule energy deposit. They've been waiting for decades. So far, nothing. Then there are axions. These are much lighter particles, originally proposed to solve a different problem in particle physics. If they exist, they'd be everywhere, a vast, invisible ocean of low-mass particles filling the universe. Experiments like ADMX use powerful magnets and ultra-sensitive detectors to search for axions. The idea is that in a strong magnetic field, an axion might convert into a photon, a particle of light, detectable, measurable. Again, so far, nothing definitive. There's also the possibility that dark matter isn't a new particle at all. Maybe it's machos, massive compact halo objects, things like black holes, brown dwarfs, failed stars lurking in the outer reaches of galaxies. But surveys looking for these objects, using gravitational microlensing to detect them as they pass in front of distant stars, have ruled out most of this possibility. There simply aren't enough machos to account for the missing mass. And then, there are more exotic proposals. Sterile neutrinos, dark photons, primordial black holes, modified gravity theories that eliminate the need for dark matter entirely. Each has its advocates, each has its challenges. The truth is, we're searching in the dark. Quite literally, but maybe that's the point. The hunt for dark matter reminds us that the universe is under no obligation to make sense to us. It doesn't care if we find it difficult, if our instruments aren't sensitive enough, if our theories are incomplete. It simply is, and somewhere in the mathematics and the experiments, in the rotation curves and the lensing patterns, the answer is waiting. So why does this matter? Why spend billions of dollars, decades of research, countless hours in underground laboratories and at telescopes, searching for something we can't see? Because dark matter is a humbling reminder. For all our technology, all our scientific progress, all the knowledge we've accumulated over centuries, we still don't understand 85% of the matter in the universe. We're living on a tiny island of visible matter, surrounded by a vast ocean of darkness. And everything we are, every star, every planet, every living thing, exists because of that darkness. Dark matter shaped the universe. It gathered gas into the first galaxies. It allowed stars to form. It created the conditions for planets, for chemistry, for life. Without dark matter, the universe would be an empty, formless void. No structure, no galaxies, no us. And yet we don't know what it is. That's both terrifying and exhilarating. It means there are still frontiers, still mysteries that resist easy answers. It means the universe is stranger, deeper, more complex than we ever imagined. And it means there's work to do. Somewhere, a detector deep underground might register its first signal. Somewhere, a new experiment might unveil the nature of these phantom particles. Somewhere, a young scientist is looking at data that will change everything. Or maybe not. Maybe dark matter will remain elusive for another century. Maybe the answer lies in mathematics we haven't invented yet, in physics we haven't discovered. But that's okay. Because the search itself is what makes us human. The willingness to look into the darkness and ask, what's there? The courage to admit, we don't know. And the determination to keep searching anyway. Tonight, as you look up at the stars, remember, you're not just seeing light, you're seeing the visible tip of something vast and hidden, a cosmic web of invisible threads connecting everything. We are, all of us, embedded in mystery. And maybe that's exactly where we're supposed to be. Thank you for drifting with us through the deep science tonight. Until next time, keep looking up and questioning everything.